Yeah, I think we can get started. Someone just asked on the Slack channel. So there's going to be a book giveaway for my machine learning book with Sarah on Thursday if you want a book for free at 4. All right, so let's come back. So we're going to continue where we left off before the break, which is with working with text data. So far we had categorical and continuous features, and now we'll talk about basically how to work with long free texts. There's different kinds of text. So we had, for example, the name in the Titanic data set. The name is sort of not really the way that natural language works because they're usually relatively unique. Someone pointed out that if you check for Mr. or Sir, something in the name, then that gives you some accuracy. But usually when we talk about text data, what we mean is like long free text, like an email or a book or a product review. And so these are very different from the numerical data we had so far because the text has it's not numbers, it's strings, and they have varying length, and they can be very long. And the length doesn't necessarily inform us a lot about the content. So we need to have a way to break up or transform these string data into some numeric representation. So let's say we want to do spam detection, for example, just from the text of an email. So we start off by just having a string. So each sample now is one string. So let's say one of our samples is the string, this is how you get ants. And so now we're going to transform this to numeric representation using the back-of-word feature extraction. The first step is to break this up into words or some normalized form of words, which is called tokenization. There's in the natural language processing community, there's a lot of very complex ways you can do this. We do something very simple. We basically split by white space and then lowercase everything. And this gives you sort of normalized words that we call tokens. Then you do this for each text in your training data set, and you build a vocabulary. So this will basically give you something like a dictionary of all English language, which might have some domain-specific words. For example, if you do movie reviews, you might have a lot of actor names in it and movie titles. So once we build this whole vocabulary, we can encode each individual sample. And the way we do this is, for each word in the vocabulary, we count how often does this word appear in our sample. So here we had the sample, this is how you get ants. And so most words in the English language don't appear in the sentence. So they're all 0. The word ants appears once, the word get appears once, the word you appears once. The word this appears once too. And none of the other words appear at all. So we have a fixed length vector now, which is as long as the vocabulary size. So that's usually like tens of thousands or hundreds of thousands of entries. And basically all of them are 0. As Alex mentioned in the beginning, we don't really want to store all these zeros because it will be very wasteful. So we use a sparse matrix representation that only stores the words that actually appear. This is called the back-of-word representation because you only count the absence or presence of words. So it's kind of shoving all the words into one big bag, and you don't really care about the order. So no matter what the order is of the words, this will give you the same representation. So now we have a very large representation, but it is like a numeric representation of the data, and so now we can do any kind of machine learning with it. So let's show how to do this with Scikit-learn. So here I have X, which has 2 data points. One is the string, some say the world will end in fire. Second one is, some say in ice. So I have 2 data points. And now I can use the count vectorizer, which implements the back-of-word encoding. So this is a transformer. So we instantiate it, and then we can fit and transform data. So fit just builds this vocabulary. This is a very small data set, so it's only has like, I don't know, we'll probably see, only has a couple of words in it. Usually, as I said, this will be tens of thousands or hundreds of thousands. So here we only have these couple of words and fire eyes in, say, the will word. They're sorted. And I can use the transform method, which will give the numeric representation, which is a sparse matrix. Again, the rows are samples, so we have 2 rows, and the columns are the different features. Each feature corresponds to the frequency of 1 word. There's 9 words in a dictionary, so X has shape 2 times 9. And there's 12 words in total, and so there's 12 non-zero elements in the sparse matrix. Here's sort of, you can make this into NumPy array with 2 array, and so you can actually look at all the entries. And I'm not going to go through all of this, but you can see that and fire appear in the first one, eyes in the second one, in, say, and some appear in both of them, and then the rest appear only in the first one. So here, everything is 1 or 0. It could be any larger integer count if a word would appear multiple times. And so, as I said, if you basically, there's a method called inverse transform, which tries to go from the output back to the input. And here in this case, you only recover which words are present because the order is not preserved. So if you want to try to interpret the back-of-words representation of X, you can only see that the second row had eyes in, say, and some, but you don't know the order. There's a couple of variants of this that I want to discuss. So this very basic back-of-word actually works reasonably well in many cases. So one modification of this is what's called TF-IDF encoding. This is basically a rescaling of the representation. So you start off doing exactly the same thing, but we want to give less weight to words that appear very commonly. So the word the, for example, is probably not very informative. And so we might want to have our classifier pay less attention to it. So TF-IDF stands for term frequency inverse document frequency. And so term frequency means how often does a term appear in a document. And inverse document frequency, so document frequency means how many documents does it appear in. And so the actual formula, is it here somewhere? No. The actual formula doesn't matter that much, but basically you divide the counts of each word in a document by the logarithm of the frequency over documents. So if something appears basically in all documents, it's going to be downweighted a lot. You can think of this as soft stop words. So stop words are words that appear very often and you often want to remove. This does something similar, but basically the more frequent something is, the less important it is. What this also does is it normalizes. So basically it applies to normalizer, which makes everything, each row, unit norm. And so here you can see the result of transforming the same text again. So the zeros and non-zeros are the same as before because the same words appear. But so you can see there's fractions. That's because we normalized everything. So you see in the second row, the numbers are bigger than in the first row because it's shorter text. And so because there's fewer non-zero entries, and because it's normalized, they're larger. And you can see that in for the first row here, the terms or the words that appear only in the first row get 0.39, whereas the ones that appear in both get a 0.28. And for the second one, the ones that appear only in the second one get a 0.63. The one that appear in both get a 0.45. All right, so basically we're just downweighting stuff logarithmically that appears very often. And sometimes that helps, sometimes it doesn't. It depends a lot on your data set and yeah, the structure of the data. Another modification of this basic bag-of-word representation is using bigrams, or more general engrams. The idea here is that we recover some of the information of the order of the words. So, for example, for some words, the order is really important. For example, if you say not and then a word, it means the opposite. So you really want to capture this. If you have a sentence and you know not appears somewhere, but you don't know where it appears, you have no idea what the sentence means. And so what you try to do with engrams is you look not only at a single word, but you look at pairs or higher tuples of neighboring words. So if you start with a string, this is how you get ans. The 1-grams or unigrams are just this and is and how and you and get and ans. And 2-grams are all pairs of two neighboring words. So it's this is how you get ans. So you can think of it as like a sliding window of 2 that goes over the whole text. And you can do this for arbitrary length. And so you can take all the overlapping windows. Very typical values of these are like 1, 2, 3. The thing is, if you have a very large corpus, these can grow very quickly. So basically, they grow exponentially in size unless you do some stuff to prune down the number of words. Because if you have a million single words, then you have often something like a million squared, 2 grams, and a million to the power of 3 grams, and you can't really store that. Yeah?
Can these 2 grams or 3 grams cross sentence boundaries?
Yes. In the Scikit-learn implementation, yes. Because basically what we do is just we do the tokenization step, which is we just split by white space, and then we do a sliding window over these tokens. I'm sure you can find libraries that have implementations that are more fancy than that. So yeah, maybe I should mention there's like NLTK and Spacey are two like standard libraries to do more sophisticated stuff with text. And sometimes they can give you some boost in performance. But this is sort of the very simple method, and it gives you a reasonable baseline. So to do engrams, you can use the engram range parameter, which gives you the minimum and maximum length of tuples that you want to look at. So engram range 2 means get all the bigrams. So minimum length 2 and maximum length 2. I do this on the fire and ice. And these are the features that are extracted, and in fire, in ice, say in, say the, some say, and so on. So these are all possible 2 grams. Actually, because this is like very short, very atypical text, the dimensions doesn't get much bigger. But if we use unigrams and bigrams, so here I do engram range 1, 2. And so I look at all unigrams and all bigrams, so this is this. Now I have twice as many features. So yeah, more commonly you get more something like nearly a square. So you get a lot more features. One way to reduce this down again is to look only at things that appear at least 10 times or something like that. Then you can bring down the number of features again. So another way to encode text data, in particular if you have something like names, is character engrams. So character engrams do the same thing as we just did with words, but with characters. This is usually not super helpful for normal text. It's helpful, yeah, for names, or if you want to find out the language of something, or if you want to categorize words into whether they are a name or not a name, for example. And you can do that by just setting the analyzer equal to char. So by default, it's word. You can set it to char, and then it's going to be a character analyzer. Sometimes that's also helpful for text if there's a lot of misspelling or if there's a lot of obfuscation, like people using using numbers instead of letters, for example. You can get the common word stamps by looking at character engrams. Usually you take more than one or two. You take like a sequence of like 5 or 6 characters. And so here's all the bigrams for the some say the world will end in fire, some say in ice. And yeah. So a lot of them look like they are one, but they also have a white space next to it. So what I'd like you to do as an exercise is compute the bigrams and trigrams from the standard of Python, and treat each line as a separate document, and then compute the TF-IDF encoding of the data. And find out what are the things that have the highest TF-IDF. And so here's the text. You just need to split it by new lines so you get separate documents. And so I'll give you like 5 minutes for that. So all right, let's have a quick look at the solution. So here we're splitting the Zen by new lines. And then for bigrams, trigrams, and fourgrams, we look at what's the most common engram. So we create a count vectorizer with engram range where minimum and maximum are the number. We transform it. And then, so the counts gives us just a back of word representation. We do sum x is equal to 0. This gives us the overall counts and the whole text. And then doing argmax gives us the most common one. So the most common bigram is better than, most common trigram is better than, and the most common fourgram is if the implementation is, because that is the only fourgram that appears twice, I think. So then for TF-IDF, we try with norm L2 and with norm equal to 1. So with norm L2, that means basically long texts get penalized, because everything is given the same length of the representation. So there's readability counts that has counts once. Counts doesn't appear anywhere else, so the inverse document frequency is very high because it doesn't appear anywhere, and because it appears once out of 2 words. So because it's very short and the word doesn't appear anywhere else, it's very high. I think this is the argmax that's returned now, but I think the same is true for readability. Readability also, doesn't appear anywhere else. So, I mean, the argmax is not, it's ambiguous. If we don't do norm equal to none, we don't get the things relative to the size of the string. We just get sort of the more absolute counts. And then we get special, because special, where's special? Special appears only in one of the documents. So again, the inverse document frequency is very high because it's like as rare as possible. And the term appears twice in this one. So basically here, because we didn't penalize being longer, special appearing twice beats the count that only appears once. Questions? No? Okay. So, questions on Slack. So now, actually it said we do a text classification with the IMDb dataset, but actually we're doing text classification with the SMS spam detection dataset. So this is, I mean, they're both fun. So here, our dataset is a couple of SMS texts. So here are the first 10 ones. So I don't know if you folks remember texts, these are like what texts used to be. So they're really short. I don't remember the character limit, but that's like they have a very short character limit. Originally, I think now like phones do whatever. And obviously they have like great jargon and spelling mistakes and yeah, they're generally slightly weird English. I think these are from the UK, but I'm not entirely sure. There's dollars in here. But you can see that a lot of them are like just sort of normal texts or what counts as normal. But then there are some that are clearly spam. So here, free entry in a 2-week competition to win blah, blah, blah. And had your mobile 11 months or more, you are entitled clearly spam. And so we want to detect whether an SMS is spam or not. Yeah, here you can see sort of what we have this data set, and there's 0 is ham, so it's normal message, 1 is spam, so it's a spam message. There's 4,800 normal text messages and 747 spam messages. And so both x and y we just have as a list of strings. Sorry, x is a list of strings, y is a list of zeros and ones. As always, we split our data set into a training and a test set. We set the test set size here to the value it's by default anyway. Because this task is pretty imbalanced, so there's like, what's this? 7 times as many ham than spam messages. So it's probably good if we stratify to keep this ratio. It also means that when we measure accuracy in the end, well, we maybe not want to use actually accuracy because accuracy will be hard to interpret, and we might look at different metrics. All right, so now we're going to use the count vectorizer with the defaults, which are only using 1 grams. We fit on a training set, and then we transform the training in a test set. You can check out how big the vocabulary is. And actually, it's really small. It's only 7,500 because we only have very few samples, and they are all very short. So pretty small vocabulary. So this is the size of our training set, 4,000 something samples with 7,500 columns. It's also interesting to look at what are these features that are actually extracted, so what are the words that are found. You can see that the first couple of words are all numbers. I guess some of them might be phone numbers even. I'm not sure how informative these are, and we could think about trying to get rid of them. If you look somewhere in the middle here, you can see that these are relatively normal English words. I don't see any really obvious misspellings here, actually. I mean, you see several forms of the same word, crash, crashed, crashing. I'm not sure what crazy-in is or what this is, but generally looks like normal words. So we also transform the test data set, so we have 1,300 test samples. Obviously, it names number of features. Now that we have this numerical representation of the data, we can just apply any scikit-learn model. As we mentioned before, linear models are particularly well suited to text data. In particular, here you can see that we have about twice as many features as we have training data points. So we could totally overfit everything here if we wanted to. And yeah, so having something simple like a linear model might be a good idea. It's a binary classification task, so we use logistic regression. So we fit it on a training set. And now I use the score function on test set. And you can see, okay, so it's 98%, 98.5% accurate, so it's very accurate. Even though there's like the strong class imbalance that was like 7-to-1. So, okay, I want to calculate what the default rate is. Possibly. But yeah, so this is clearly way above that, and so we more or less solved this task. Depending on how important it is that we actually detect all of the spam. But I mean, this is doing pretty well. We can compare this to the training sets. On the training set, we're basically near perfect. We haven't overfitted everything. If we completely overfit, we had would have 1.0. We could try to think about making the model a little bit simpler and maybe get a little bit better on the test data set. But before we do this, we're going to visualize some of the coefficients. So what I'm going to do is I have the classifier and the feature names from the vectorizer. And we look at the coefficients, the linear coefficients, like these guys. So there's one coefficient per word. And we're going to look at the ones that are largest in magnitude, so the highest and the smallest ones. And then we're going to plot them. And we get something like this. I'm not sure how well you can see this. So the negative ones are associated with the class 0, so with the not spam class, and the blue ones, or the positive ones, are associated with the spam class. First thing that I see is that the blue ones are much bigger than the red ones, so it's easier to pick a word that's indicative of being spam than being indicative of not spam. And so you can look at this end here, and it will tell you what are the words that are most indicative of it being spam. And they're txt, UK, I guess because it's some URL, ringtone, reply, call, text, one, chat, stop, new, claim, service, mobile, free, cost, message, price. Yeah, and then some more URL stuff. And so here are the ones that are indicative of not being spam. Like there's some shorthands, there's pronouns like my and he and sorry, which is probably not often in a spam message. And so, okay, so this is like a relatively easy data set. And even with this very small, relatively small data set, we can do a pretty good spam detection. So one way to try to regularize the model, make it simpler, is to remove some of the features. In particular, here I use min_df equal to 2, which means I only include words that have a minimum document frequency of 2. So a thing that appears only in one text message is very unlikely to be informative. So if I do this, let's see if I actually got better or worse. I got a tiny bit worse on the test set actually, which is somewhat surprising. But I want to see how many features there are. So there's now only 3,400 features, so it's much less than before. Maybe I actually want to also look at some of the.
So that is just if it occurs twice in one document?
No, in a whole corpus. Basically, I kicked out everything that appeared only once in the whole training corpus, because I feel like I can't really learn anything if it appears only once. And basically, half of the words appeared only in once. And so you can see, oh, wow, some of the, interestingly, some of these numbers are still there. So I guess they were used in multiple spam calls or messages. But sort of, I mean, the test accuracy is like a tiny bit lower, but I would probably trust this model more just because it uses much less features and is nearly as good. We can also do a visualization of the coefficients. And yeah, actually, I don't really see a big difference. Because the ones that are important, that were all the ones that appeared more commonly anyway. Yeah?
If one wanted to assign a much bigger penalty for classifying a non-spam message as spam than the reverse situation, I assume it would be easy to do that?
Yes. So there's multiple ways to do this. The easiest way is basically to change your interpretation of the outcome. So right now, like logistic regression gives you a probability estimate. And right now, it thresholds the probability as 0.5. So if the probability is higher than 0.5, you say it's spam. And the easiest way to achieve what you want is basically to change this threshold. Right now, you have to do that manually, but I think that is sort of the best way to do it. And this way, you can, I think we talked about this a little bit later, but there are several ways you can think about how important are false positives versus false negatives. And depending on what your trade-off is, or on what kind of cost you assign to the different kinds of mistakes, you can adjust your threshold. So yeah, I wouldn't actually put this in the machine learning model. I would put this in the decision making after the machine learning model. All right, so here's like a summary of sort of machine learning with text, but also with all kind of different modalities that are not just standard numeric data. So basically, you want to use the vectorizer, like the dict vectorizer or the count vectorizer here in this case, and create feature vectors, and then we can use the feature vectors together with some supervised information, some labels, to fit the model. And of course, we need to use the same vectorization method for any new documents. Okay, cool. So as a result, I would like you to, as an exercise, I would like you to use the TF-IDF vectorizer instead of the count vectorizer. Compare the results. Are they any better? Are they any worse? How are they different? How are the coefficients different? You can look at the largest coefficients again. And how does changing the min-df and the Engram range for TF-IDF and count vectorizer, how does this change the outcome? And how does this change the important features? And so maybe I'll give you like 10 minutes to play around with that. All right, let's have a look at the solution. So, I mean, here the code basically doesn't change for TF-IDF vectorizer. We just do the same thing we did before with the count vectorizer. We instantiate it, we fit it on the training data, then we call the transformation of the vectorizer on the training and the test data. And then here I fit the logistic regression model, compute the scores on training test data, and look at the coefficients. So here you can see that the model actually performs quite a bit worse, though there are some parameters. Actually, let me try this. Well, if you change parameters in logistic regression, which we didn't do, then you can get about the same performance. So it's sort of, there's a lot of different things to tune, basically. So with the default parameters of the logistic regression, so you get 97% accuracy, which is worse than what you got before. But yeah, so here, what I did now is I decrease the regularization a little bit, and then you get something like this here, which I can't really interpret. So now let's see what happens if we change the MinDF and Engram range. So I'm just going to run through one thing here. Like you can see by yourself how this changes the number of features, for example. Let me actually do this here. So here, wow, I only got 1,000 features if I use Engram range 1 to 3 and do MinDF equal to 10. Let's see what happens if I do MinDF equal to, let's do 3. 3 seems more reasonable. Then I have about as many features as I had originally with the 1 grams. You see that in the top features, not many of them show up. Your call, 1, 2, RU show up and have to, but for the spam ones, nothing really shows up. I think there was some when you used MinDF equal to 10. Yeah, you have, which is, yeah, makes sense. You have 1 XX. All right. Questions about this? All right, so yes, so basically adding more Engrams will make the dictionary much larger, but increasing minimum document frequency, you can make it a little bit smaller again. So if I don't use minimum document frequency, you see I get 83,000 different 3 grams, and I get very specific features like ringtone king. Okay, so I guess that's enough for doing text classification for now. So what we're going to do next is talking about model evaluation, in particular cross-validation and different ways to score a model. So we saw already accuracy is maybe not always the right answer for classification, and we also saw that the results you get depend a lot on how did you split your data set. So what we did so far is we used our data set, we split it into training and test part, built a model on a training part, applied the model on a test part. So as we saw, it's kind of not really that robust because changing the split changes the outcomes quite a bit. Also, it means you have less data to train your model, because if you want to have a good estimate of how well your model does, you want to have a lot of test data, but it means you have less training data, which means that your model will probably be worse. So the standard technique to sort of combat this and get a more robust estimate of how well a model does is called KFold cross-validation. The idea here is that we split our data into so-called folds. So let's say we use 5 equally sized parts. So instead of doing training and test, we do these 5 parts. And now we build 5 different models. For the first model, fold 1 is the test set, and the remaining 4 folds are the training set. Then I built a second, so I built on a training set, I score on a test set, I get 1 accuracy value or whatever my metric is. Then I built a second model for the second split where fold 2 is the test set. And again, I get my score. And so I repeat this 5 times. Now I have 5 different evaluations of my model. I can see sort of what's the difference in these. Does it depend a lot on the split of the data, what the outcome is? And I can also compute the mean of them, for example, or the median to have a more robust evaluation. What's also great about this is that splitting in this way, each data point is in the test set exactly once. If you split your data just once and randomly, you could be very lucky and all the hard examples are in the training set. Or you could be very unlucky and all the hard examples are in the test set. And so there might be a lot of variance. But if you do five-fold cross-validation, then all the data is in the test set exactly once, and in the training set exactly 4 times. And so you can average out a lot of the variance. Can anyone come up with a shortcoming of this method? Oh, yeah, if the data is ordered, then this is not a good idea, yes. Because then you shouldn't split it randomly. Ordered data is a whole thing by itself.
Takes longer?
Yeah. So here, this takes 5 times as long. So usually people do 5 or 10-fold cross-validation. Or you can also do repeated cross-validation, where you do 5-fold cross-validation, but shuffle the data 5 different times. So you have 25 evaluations. So you spend at least 5 or 10 times as much time. Also, the outcome of this normally is not a model. It's like 5 scores. So if you want to actually train a model, usually the way to do it is retrain a model. This only tells you how good is a model. It doesn't really provide you a model. Right, so now let's apply cross-validation to the nearest neighbor classifier on the iris data set, just to get a feel of how this works. So basically what we want to know is how well does a k-nearest neighbor classifier do on the iris data set. So we load our iris data set, we have x and y, and we have the classifier. Actually, do we actually want to do this? Well, all right, let's do this. So the data in iris is sorted. So to get rid of some like silly side effects, we're gonna shuffle it real quick. And so if you wanted to implement cross-validation yourself, it's relatively easy. Where relatively easy is like 15 lines. So basically what we're taking is we take, don't want to run through this. Well, I think you can read the code by yourself. But like we create a task mask, which basically is full size once, or full size times true, and then the rest is negating that gives you a test set. Sorry, gives you a training set. And so here is the mask we get. So here the Boolean mask for a test set is the first 30 samples in the first split, the second 30 samples in the second split, and so on. So the white is the data that's in the training set, and the black is the data that's in the test set. And so for each of them, we computed a score. So this is accuracy, and so we have 5 different accuracy values, and you see they go between 90% and 100%, and they have a mean of 69%. So this is also, so on a real application, I would be slightly concerned because that's a pretty big standard deviation. So yeah, that is because there's not a lot of data. And because the model is pretty complex, I think. But so if I only told you it's 96%, you might think, oh, this is great. But if I tell you maybe it's also just like 90%, you might think differently about the model. So having an uncertainty estimate is cool. Okay, because this is such a commonly used method, clearly we have a function for this in Scikit-learn. So, which is called Crossvalidation score in the model selection module. And the Crossvalidation score function takes a classifier. Here, this was an instance of our k-nearest neighbors, and the data x and the labels y. And then it computes the cross-validation accuracy. So by default, it uses 5-fold cross-validation. We can set CV equal to a number and do by default that's 3-fold. We can do 5-fold or 10-fold or whatever fold we want by setting a number. Yeah?
So when you do this a bit, do you want to keep the ratio of each category in the original data?
Yes, the question is, do you want to keep the ratios between the categories? Yes, you do. This called stratified cross-validation, where basically, yeah, you make sure that in each fold you have the same fraction or the same ratio between the classes as in the original data set, and that's what we're doing by default here. So whenever you give it a classifier, then it'll do stratified cross-validation. So if you want more control over what's happening there, there's some cross-validation generators that are used to generate these splits. They're all in the model selection module as well. So the standard ones are KFold, which is just splitting basically arbitrarily, stratified KFold, which takes the classes into account, Shufflesplit, which does repeated random splits. We actually also, it's not released yet, but we also have repeated KFold and repeated stratified KFold. This is not. So, and these iterators have a split method, which take the data and the targets and then generate some splits. So here, for example, this is the stratified KFold with 5 splits on the iris data set. It's maybe a little bit hard to read, but the indices for a test set in the first fold are the first 10 samples, then the samples from 50 to 60, then the samples from 100 to 110. It's maybe easier to look at this as a mask. So this is sort of how the test mask looks on the iris data set. So the point is that the classes are sorted. So this here corresponds to the first class, this here corresponds to the second class, and this here corresponds to the third class. And in each fold, you want to have a little bit of each of them. Yeah?
How do you cope with the problem of getting 3 different models?
What's the problem? So
each of the folds gives you a different model.
So the goal of cross-validation is to tell you a given model with a given set of hyperparameters, how good does it do on a given data set? And it gives you an answer, and it gives you like k different accuracy values, which you can aggregate. But you don't get a model out of it. So if you want a model, for example, you could train on the whole data. Like if you say, oh, this result is good enough, I want to now apply this in my service, in my research, whatever. I train on the whole data set again, and then I have a model. But this is something that allows you to judge, is this a good model or not? And it allows you to do that more robustly than just doing a single split. So here's the comparison against, so the top one is Shufflesplit, stratified KFold. This one is KFold, so KFold just takes the first 30, then the second 30, and so on. So that's not great on the iris data set because it's sorted. I mean, if you just take more splits, it looks like this. So Shufflesplit is also kind of interesting. Shufflesplit allows you to just repeat as many times as you want with a given test set size. So here, what we're doing is basically we repeat 5 times, and we always take 20% of the data as test set, just randomly. And so we can instead also do it just like, instead of 5 times, we can do it 20 times and just randomly sample more. This is nice because it decouples the size of the test set from the number of repetitions. But it also means that the same data point can, like, not all the data points are in a test set the same number of times. So for that reason, I prefer repeated KFold cross-validation. In repeated KFold cross-validation, I do KFold, and then I shuffle the data and then do KFold again multiple times. So, and maybe just as a very quick exercise, and if you want to use any of these generators in cross-val score, you just need to instantiate the method, instantiate the this generator and give it as a CV argument. So the CV argument can either be a generator or it can be an integer. And just as a very quick exercise, you can use cross-validation on the iris data set, just a standard KFold cross-validation with 3 folds and see what happens. All right, so if you ran this, you instantiated a KFold model with three splits, and you pass this to cross-val score. Then the result is 0, 0, 0. Why? Yes, the test set is always an unseen class. So there, you split it into thirds, and each third is a different class, so that there's no overlap between the training set classes and the test set classes. So it can't do anything. So you can get rid of this either by shuffling the data, or by using certified KFold. But by default, KFold does not shuffle in Scikit-learn. And that gives you these nice results. All right. So next, I want to talk a little bit more about model complexity and selecting parameters of the model. We already talked in the beginning about how the number of neighbors changes the behavior of the k-neighbors classifier or k-neighbors regressor. So here's again like some illustration. It shows you, this was sort of, I think, the thing that we used in the beginning, where green is your training data set. The function is like this periodic function that goes up. And here in red, I show different fits. And if you use 2 neighbors, you get this super wiggly function that is way too noisy. If you use, but it goes basically through nearly all of the training data points. If you use 5 neighbors, you get a function that is pretty smooth and pretty well approximates the true function. And if you use 20 neighbors, we basically smoothed away the periodicity, at least partially, and we're sort of left mostly with this overall trend. And so this is, so maybe you would say the model in the middle has about the right kind of flexibility. The one on the left is too flexible. It's overfitting the data. It's focusing too much on each individual data point, whereas the model on the right is sort of too rigid and doesn't really capture all the variation in the data. So these are sort of the 2 concepts of underfitting and overfitting. Underfitting means your model is not complex enough, and overfitting means it's too complex. And there's sort of a general trend in how training and generalization relate to this. So if you to model complexity. So if you have a model that's very simple, so it's very to the left. Let's say this one is sort of very simple because it's very smooth. Then you will do badly on training and test set, but you will do equally badly. You can't really capture the variation in the training data set, but you don't focus too much on a training data set. So you're equally badly on training and test data set. if you allow your model to be more and more complex, the training accuracy, or whatever your metric is, will go up and up and up. And if you allow the model to basically learn the data set by heart, you're going to get 100% accuracy on the training set. As the model complexity increases, you also start to get better and better in generalization performance, because you're able to capture more of the variance in the data and more of the structure. But there will be a wider and wider gap between your performance on the training data set and your generalization performance on the test set. And so at some point, if you make your model too complex, the generalization performance will actually go down. And so somewhere there's a sweet spot of where the model has the right complexity that generalizes the best. And so a lot of like parameter tuning and finding the right model is about finding the sweet spot where the model can capture enough of the structure of the data, but doesn't overfit. But that's sort of more a mental image. It's not. So how to do this is usually pretty tricky in practice. So here we're doing the thing. I'm running this toy data set with the sine wave again. Didn't I want to plot it? I thought I plotted it. Well, okay. So I'm doing the sine wave, and I try k-neighbors regressor with different numbers of neighbors, 1, 3, 5, 10, and 20. And so basically the way that I want to find a sweet spot is by doing a brute force search. I try each of them, and I do cross-validation, and then I compute the average cross-validation score, and then I might want to pick the one that has the best cross-validation accuracy, R square. So this would be this one. So maybe I said 10 neighbors is the best. All right. There's also a function that can help you to visualize this a little bit better, which is the validation curve. Not validation plot. So here you can see how the, it's not accuracy, is it? It's actually R squared. How this changes with the number of neighbors, and you can see this kind of reflects the curve that I had up in this sort of cartoon. And so if the model is very simple, which means a very high number of neighbors corresponds to something that's very smooth, then the model does pretty bad both on training and test data set. And then if I increase the number of neighbors, the model becomes better and better. And then probably the best model is somewhere here. And then if I increase the number of neighbors even more, then we're overfitting. The accuracy on the training set goes way up. The accuracy on the test set goes way down. So in general, a model usually has many parameters that we might want to search. And so we have an example of a different class that we're not actually going to go into in detail. So more about that later is a lie. But so the support vector regression, for example, has two important parameters, C and gamma. And so if you want to adjust these parameters, you do a brute force search over all possible combinations usually. And so I can do a cross-val score for each of them. And then I can see that this one is probably pretty decent. Or maybe this one. And so because this is such a common pattern, again, we have a helper for this in Scikit-learn, which is called grid search CV. grid search CV is what we call a meta estimator because it takes a model, for example, support vector regression or linear regression or whatever model you have, and it creates a new model or a new estimator that uses this model internally, but also finds the best parameter for you. So the way this works is you instantiate the grid search CV with the model for which you want to adjust the parameters, and then a param grid. And the param grid is a dictionary which has as a key the parameter names. So for the support vector regression, we have C and gamma. And then as values, all the different parameter values you want to try. And what it does is it searches the product space of these two, so all possible combinations. And then you can also specify a cross-validation method. So here I think we did just KFold. And okay, we tell it to be verbose so we see what's happening. So this just constructs a new estimator, a new model, built on the support vector regression, which does internal cross-validation to find the best parameters. So when I call fit, what it does is, for each possible combination of these parameters, it does the cross-validation. It finds the parameter that has the best cross-validated average score, and then it refits the model on the whole data set that I pass it in. So here, I pass it all x and y, so it will refit the whole model on x and y. And so here it tries all possible combinations, blah, blah. Sorry about that. And then, because the grid search CV is an estimator, it has fit and predict and score. And so if I want to make a prediction now, I can just call predict. And predict will use the best model, or the parameters that the model with the best parameters as found by cross-validation trained on the whole data set. So we actually don't have to worry about what the best parameters are. We can just call predict or score. If we want to find out what the best parameters are, we can look at the grid.bestparams attribute. So C equal to 10 and gamma equal to 1 were the best parameters. And you can also look at what the best cross-validation score is and grid.best score. So that's the mean over all the cross-validation folds. So what you still need to do here is you need to know which parameters to search over and what the possible candidate values are that you want to search. And there's a lot about that in the documentation and the examples. And it's basically something that is sort of expert knowledge that hopefully we've done a good job in the documentation to explain. So for example, for these particular C and gamma, you use a logarithmic search range. So I didn't do 1, 2, 3, 4, 5, 6, but I did something that is like exponentially increasing. So the thing is that you might be tempted to use the best cross-validation score and say, this is how well my model does. The problem is, this is too optimistic because we trained now, I don't know how many combinations there are. What did it do? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we did cross-validation 9 times. And this is the best out of these 9. And so that means I use this score to select the best. And so this means it's not really an unbiased estimate of how well I will do on new data anymore, because I selected the best. And so if I actually want to have a good estimate of how well this model will do in the future, I need to use an additional training test split. Before we go into this, actually, I want to show you how to analyze more the results of grid search. So we have this best score and best params, but we also have CV results, which is a dictionary that contains a whole bunch of things. So it contains, for each split of the data, the fit time, for each parameter combination, and it contains the mean fit time, the standard deviation of the fit time, score time, and so on, the parameter settings, and for each of the splits that we have, the scores of the split. So this is a big table. So the easiest way to look at it is using pandas. So from this dictionary, I create a pandas data frame. And so each row here corresponds to one combination of the parameter C and the parameter gamma. And so you can see the scoring time and fit time and where's the mean? Yeah, the mean test score and the mean training score, for example. And so here we can look at the ones that have so these are the 5 samples that have the highest test score, if you're interested in the ones that have like generally good parameter settings. So I subsetted the table here with just the parameter C and gamma and the test score. Actually, maybe I want to do the train score as well. And so I sorted them by the test score. Wow, they have widely varying train scores. I guess these are also widely varying test scores. I mean, this is really a lot better than the other ones. So I probably would use this one. Yeah. All right, yeah, so as I said, this is not really a good way to evaluate. So this is a good way to pick the parameters, but it's not a good way to evaluate how well will this do in the future. Another way to think about it is, let's say I use a model that has some randomness in it, and I train it 1,000,000 times, and then I look at all the outcomes, and I take the best one. This is probably just the one that randomly did best on this particular test set. That doesn't mean it will randomly do best on future data it'll see. So, as I said, the solution to this is to have a separate test set. So we split our data into training and a test set. Then we do cross-validation to find the parameters only on a training set using grid search CV. And then we do a final evaluation on a test set to see how good does this best model generalize. Sure. Okay, so I have a flow chart for doing this too, but it's not in the slides, unfortunately. So you start with your data set, and you build a training set and a final test data set for evaluation. You use the training set to do cross-validation to find the parameters using grid search CV. Then, using the best parameters, you build a new model on the whole training set. Then you want to know how well does this model generalize to new unseen data. And so you do basically one final evaluation on the test data set that you held out. This will give you an unbiased estimate of how well the model with these parameters will do in the future. The question is, did we end up where we started? Kind of, because we are now using a single split into training and test data in the outer loop. So if you want to go crazy, you can replace this outer loop by another cross-validation, so then you call it nested cross-validation. But then again, the outcome is not a model, but the outcome is how well does a model on which I tuned the parameters perform in the future. Because each inner split can find the best different settings of parameters, and yeah, things get kind of complicated then. So yes, using a single split of the data is not ideal, but it's kind of tricky to work around that. The idea here is that you look at this test data only once. That still means it has a lot of variance, but at least you then don't end up overfitting it by looking at it too often. All right, and so here, luckily, I mean, what happens is kind of complicated, but the implementation is very simple. Actually, I don't know why we shuffled it here. I guess we want to shuffle. So if you don't want to shuffle explicitly, you could just write 10 here instead of instantiating it. But so what you do, you split your data into training and test set. You define your parameter grid. You define your cross-validation if you really want to. You instantiate grid search with the model and the parameters. You fit the model on the training set. This does all the nested cross-validation parameter search. And then you do score, and score will use the model with the best parameters trained on the whole training set, and you evaluate it on a test set. And yeah, and if you want, you can still look at the parameters that were selected. So this is sort of the, possibly not the very best you could do, but this is sort of, I think, what is good practice. What you can also do is just do a split of the data into 3 parts. This is usually what people do if they do deep learning, because training a model just takes so much time that you don't want to spend time doing cross-validation. So the minimum you need to do is basically have a training set, have a validation set to set parameters, and then have a final test set for evaluation. You can also do this with Scikit-learn, and the easiest way to do this is just use Shufflesplit cross-validation with the number of splits equal to 1. So that basically means the inner cross-validation loop only has a single split into training and validation. Then you can do the same thing, only it's going to be much quicker, but the parameters might not be as good. Actually, here there's no difference. Cool. So what I'd like you to do is use grid search CV to find the best number of n neighbors in the k-neighbors classifier applied to the digits data set. So load the digits data set, split it into training and test set, do grid search. You need to define the parameter grid for n neighbors, and then run the grid search. And please really, really try to do this before loading the data, because this is something, if you want to do machine learning in the real world, you will always have to do this. So please give it a go. All right, maybe let's continue because we're way behind time. So just to go through the solution. So we're loading the digits data set. We split it into a training and test set. Ideally, we would also stratify. Okay, if I have to. There was I think there was like a blog post somewhere about people looking at how many random states, or how often 42 is used in GitHub relative to all other numbers. I'm not sure how much you're to blame for this. Okay, so here the parameter grid is this time we only have one key and neighbors. So n neighbors, again, is the parameter of the k-neighbors classifier that we want to adjust. Here I'm trying 1, 3, 5, 10, and 50 that I just basically came up with. So these should be much smaller than the number of samples usually. And so I say CV equal to 5 to do 5-fold cross-validation, give it a parameter grid, and tell it to be verbose. And then I just call fit on a training set. So here you can see it does 5-fold cross-validation. So for n neighbor equal to 1, it wants to 1, 2, 3, 4, 5 different ones. For 3, again 5 ones for 5, 5, and so on. And then the score on the test set that we get is 98.4% accuracy, and we achieve that with number of neighbors equal to 1. So that's actually just using one neighbor is the best on this data set. Questions about this? All right. So we're going to skip 15 because we don't have that much time. So there's a method to chain the multiple preprocessing steps and classifiers, which is really awesome. It's called pipelines, and you should read up on it. We're not going to do it. Instead, I want to talk a little bit more about model evaluation and scoring metrics. So we here I just loaded digits and split it and trained a model on it. And so by default, we use classifier.score, which is accuracy. But this is a very aggregate statistic and mostly makes sense for balanced classification tasks. It's very easy to interpret, though. I mean, if I have 95% accuracy, it means I'm correct 95% of the time. At least it's easier to interpret with balanced data set. Another thing that you should definitely look at is the confusion matrix. The confusion matrix is much more fine-grained. So here, this is for the digits data set again. Here, each row corresponds to one true class, and each column corresponds to a predicted class. And so basically, this tells you how often was class I classified as class J. And so you want basically all the numbers on a diagonal to be high, because these are the correctly classified ones, and ones on the all other entries should be small. So you can also plot this. So here you can see the rows are the true labels, and the columns are the predicted labels. And so you can see that we predict, so that most of the mistakes are us predicting 1 when it shouldn't have been 1. For example, for the 8. There were 4 8s that you mistook as a 1. And there were 1, 2, 3, 4. There's 2 4s that we mistook for a 1. And so you can find out what the mistakes are. And yeah, so you see that we classified way too many as 1. We also classified a couple of things, misclassified them as 9. 0 was very easy. There's no, we never classified something else as 0 wrongly, and there's only 1 0 that we didn't classify as 0. So this gives you like a very fine-grained view into what happens with the different classes, but it's very hard to use this for model selection and grid search because you can't really compare to confusion matrices and say which one is better. There's a couple other metrics you might want to look at. In particular, precision and recall and F-score. These are all usually done for binary classification. So in binary classification, we call one of the classes arbitrarily the positive class and the other one negative. Usually the positive class is the one we're interested in. So if you do cancer screening, cancer will be the positive class. But it's like sort of dependent on the context and sort of arbitrary. But depending on which class you call the positive class, precision will be the true positives, so that's the correctly classified positives, divided by everything that was classified as positive. So true positives and false positives. Do we have a picture here of the, no, of the binary? That's too bad. So TP, FP, FN, and which one? FP are basically the 4 entries of the binary confusion matrix. Let me just. So this is the binary confusion matrix, and this is. So, and you can, so this is the binary confusion matrix. So positive classified as positive is true positive, positive classified as negative is false negative, negative classified as positive is false positive, negative classified as negative is true negative. These are 4 numbers that are like very fine-grained information about binary classification, and then there's like a whole zoo of metrics you can derive from this. And so precision and recall are 2 that are very commonly used. And so these are basically, so precision is this entry divided by this row, and recall is this entry divided by the, sorry, this one is divided by a column, this one is divided by row. So precision says, of the ones that are classified as positive, how many are actually positive? And recall says, of all the ones that are positive, how many did I get? Recall is also called coverage because basically it's how many did I get, and precision is how many of the ones that I got are actually true. And so depending on your application, one or the other might be helpful. There's the F1 score is the geometric average of the 2. And so that kind of gives you some kind of trade-off between these 2 values. You can use the classification report to compute all of them. So these are binary metrics. So if you do this with a 10-class classification problem, such as the digits, you will get precision and recall for each class being the positive class. So if 0 is my positive class and all the rest are the negative class, then precision is 1 and recall is 0.95. Support just means the number of points in the class. And then you can average these over the different classes, and these give you different possible metrics. In particular, for imbalanced classes, these can be better than just using accuracy. So as an example, so for the digits data set, by default, it's more or less balanced, where 10% of the data belongs to each of the classes. Let's say we do a very imbalanced data set where we look at 3 versus all the rest. Now we have a 9-to-1 imbalanced data set. And now we can look at the score, for example. Here I run cross-validation with a support vector machine on this very imbalanced data set, and I get 90% accuracy. Is this a good result? No. Because it means if I always say it's not a 3, I get 90% accuracy. So one could also argue it doesn't really tell us a lot, the 90%, because it might actually be sort of, the model might have learned something or it might not have learned something, but from the 90% alone, we can't really tell. But yeah, so if I use a dummy classifier that just predicts the most frequent class, I also get 90%. So a different way to look at this would be to look at the F1 score or precision and recall. What I often find even more helpful is to look at the ROC curve. So what the ROC curve is, it plots the false positive rate versus the true positive rate. True positive rate is the same as recall. False positive rate is false positives divided by false positives plus true negatives. So these are slightly different numbers than precision and recall, but they have relatively similar interpretations. But so what this curve does is it doesn't look at only computing precision and recall or false positive rate and true positive rate, but it looks at the continuous output of a classifier. So here actually I tried the support vector machine with different values of gamma, and I look at the decision function. So the decision function, I mentioned it earlier, gives you a continuous uncertainty estimate. So this is just this is a binary task. So here I get a number somewhere between positive infinity, negative infinity. That tells me how much the model thinks it's class 0 or it's class 1. If I call predict, it'll give me 0 whenever the decision function is below 0, and 1 whenever the decision function is above 0. But often I don't, so this cutoff is not a good choice, as I mentioned earlier. So depending on, is it more important to have a high recall or a high precision? Do I care more about getting all possible positives or not making any positive mistakes? I might want to use a different threshold. So what the RC curve does is it goes through all possible thresholds. So basically, at each value that appeared in a decision function, I do a threshold there. And for this threshold, I compute the recall and the false positive rate. And so this gives me a continuum of all the possible trade-offs between true positive rate and false positive rate that I could have. And so here I drew these for 3 different values of gamma. For 0.1, 0.01, 0.05, and 1. And so all of the 3 have an accuracy of 90%. 2 of them have an AOC of 1, which is the AOC is a summary of the curve, which is the area under the curve. Stands actually for area under the curve. And 1 has an AOC of 0.5. So AOC of 1 means you're up here in the corner, which means you can get a false positive rate of near 0 with a true positive rate of 1. This means basically you made no false positives, but you got all the positives correctly, which is perfect classification. So what this says is there's a threshold. If I pick this threshold, I basically get more or less perfect classification for both of the first 2 settings. For the 3rd setting, I get basically a diagonal line. This is what you get for chance performance. It basically tells you whenever I'm always as likely to add a true positive as to add a false positive, because they they go in with the same slope. So all of these 3 models have the same accuracy, but some of them have perfect AOC, and some of them have chance AOC. This tells you that this AOC is a much finer grained metric to assess how good the model is, in particular for imbalanced data sets. So it is 1 and 0.5. These are independent of how balanced or imbalanced the data set is. So 0.5 will always be chance, and 1 will always be perfect. So the reason why these have AOC 1 and accuracy 90% is probably the threshold of the default threshold of 0 was not very good for this imbalanced data set. So I encourage you, whenever you do basically anything, always look at the AOC curve. You can also look at the precision recall curve, which we don't have here. That's sad. That plots precision versus recall, again, for all thresholds. And think about what kind of trade-off you're interested in. It's very unusual that a false positive and a false negative have the same cost to you.
Can you talk a little bit about the output of the ROC curve, the function that you're assigning to So this is the false positive rate, the true positive rate, and these are all the possible thresholds. These are just the unique values of the decision function, basically. So I look at all possible thresholds, so all thresholds that appear in the data, which is the decision function for each possible data point. And for each of them, I compute false positive rate and true positive rate.
Maybe a warning on multiclass.
The warning is there's no multiclass? Okay, yeah. So right now, there's no multi-class implementation of AUC. There's a pull request, but it's something like, there's many ways to do it, and there's no standard way in the literature to how to do it, I think. And so we're slightly undecided on what to do about this. But for binary classification, it's definitely an amazing tool. For multi-class classification, you can look at a PR, you can look at papers to see what kind of schemes people come up with. Yeah. But so in the end, you need to basically figure out which trade-off is important for you, and then pick a threshold that is good for your trade-off. So if you want to use this metric or any other metric for cross-validation or grid search, you can do this very easily by using the scoring parameter of the cross-val score. So there's a list of built-in scores, for example, ROC AUC for the area under the curve. And if I do this, it'll just do cross-validation with ROC AUC instead of accuracy. I could also probably do no, it's F1 macro, right? So if I put in accuracy, this is the default. You can look on the website. There's all the different options you have explained. You can also look in this built-in scorers dictionary. These are all the scores. Some of them are for classification, some of them are for regression, some of them are for clustering. There's a lot. And I think we're going to skip the exercise because we're running out of time. The exercise is about something called average per class accuracy, or which is also a nice metric, but not as commonly used. So yeah, we don't have that much. So definitely also look at the documentation on precision recall curve. That's a similar curve that's sometimes a little bit more helpful even. Do we want to break? I think we're going to break now and come back in like 15 minutes. Then we're going to talk about linear models and trees and forests. And then after that, Alex is going to talk about some unsupervised methods. So yeah, let's take a 15-minute break. All right. So I'm going to talk a little bit about two families of models next, linear models and trees. These are two of the most widely used and most useful machine learning models, and so I think it's good if you know a little bit more about them. So we're going to start with the notebook 17, in-depth linear models. So we saw before a little bit about linear models for regression classification. So linear regression was for regression, logistic regression for classification. And we want to talk a little bit more about these models and related ones. So for regression, we had this wonderful formula here that Alex drew on the board, and then I erased, and he drew it again. And it's still there. So in linear models for regression, our output y is a linear combination of the features. So we have these x test 0 is just sort of the 0th feature of a test data point, and we multiply this by the coefficient we learned, and we add these up for all possible features, and then there's some intercept in the end. And so let's look at how this works with a toy regression data set that we make here, which is 60 data points and 30 features. And actually, most of these features are sort of noisy and uninformative, and that's just sort of a synthetic toy data set. The simple method that we talked about before is linear regression. And here you can see the model that linear regression solves, or the problem that linear regression solves. It's a convex optimization problem. So here the coefficients are called W, and the intercept is called B. And what we're saying is basically that W times xi plus b should be the same as y in a least square sense. So you take the 2 norm of this, you sum it up over all the samples in the training sets, over all the i's, over all the data points we have. And you want to find the coefficients w and the intercept b that minimize this. And this is a convex optimization problem. And if you want, you can throw like a standard convex solver on this, or you can just compute this with an SVD or many other methods. And so basically what this does is it says, fit the training data perfectly with a linear model, or as well as you can with a linear model. And so you can see that here the R squared in the training set is pretty high, it's about 0.87, and on a test set is 0.21. Because it's a synthetic data set, we actually know the true coefficients of the model. So this data set was actually generated with a linear relation, only we added some noise to it, to both x and y. And so after the noise we added, or knowing the true model, and taking into account the noise with the true coefficients, we could get an R square of around 0.6. This tells us that we really overfitted the training set here, and we're not doing so well on the test set. And clearly there's like a really big gap between the training and the test set performance. So we might want to keep this model from overfitting so much. So here is a visualization of all the coefficients. So these are all the features. I sorted them by the true value of the coefficient in the true model. Obviously, in the real world, no model will surely be linear, but sort of this rather goes to illustrate more general points about the model. So if you have here, these are your coefficients, and this is what linear regression found, and so you see that many of them are much, much larger. So these were all 0. Most of them were actually 0, but linear regression found very strong effects here. So not great. Yeah, let's skip this. Or, well, maybe let's real briefly. So what you can see is also here we used if you increase the training set size, things become better though. So linear regression, if your training set is pretty big, will do well. If your training set size is about the same magnitude as your number of features, you're likely to overfit a lot. So here we had 30 features. And so if you use something like 40 samples, you get like very bad overfit. But the more data, so here we have a synthetic data set, so we can just sample more data from what we know is the model. So if we use more and more training data, we overfit less and less. And our test error here actually goes up to 0.6, which is basically the true optimum. So if I had twice as much data, I could actually learn the model. But in the real world, we can't really get twice as much data usually. Or if you can, good for you. If you can't, you still want to be able to learn. So we want to keep this model from overfitting. So one method that we talked about earlier is maybe do PCA reduce the number of features. But that's actually, yeah, so I don't like it as much, but that's one possibility. Another option is to use regularization. So the most commonly used form of regularization for linear models is what is called an L2 penalty. The model that corresponds to this is called ridge regression, and it's very similar to the model above. So in addition to this term which says predict well on the training set in the least square sense, there's also another term that says the coefficients should be small. And there's an alpha which trades off between the two. If you set alpha equal to 0, you get linear regression. If you set alpha to infinity, you get a coefficient vector that's all zeros. And by changing alpha, you can go along this curve between overfitting and underfitting that we showed before. So here, this is for the 4 different values of alpha. And you can sort of see the curve that we had before. If alpha is very large, we're penalizing a lot. We're saying the coefficients in W should be very small. And so the training set score is not the best, and the test set score also not. Then if you set alpha equal to 10, you get a test set score of 0.4, which is much better than what we got with linear regression. And if you decrease even more, you overfit, your training score is high, but your test score is low. But so really, this alpha parameter is a great way to control the complexity. We can also plot the coefficients. So here's the same plot as above, only now with 4 different values of alpha. So here, alpha equal to 0.01 is very close to what linear regression did. Blue is the true coefficients, and you can see with more and more regularization, basically all the points are drawn towards 0.
How do you determine this alpha? Is it just trying it out?
Yeah, grid search. There's slightly smarter things than grid search, but basically grid search. But yeah, you need to do cross-validation to find it. What you can also see here is that if you have a very high value of alpha, then all the large coefficients are pushed towards 0. So this is not an unbiased model. You bias all the coefficients towards 0, which is why statisticians don't like this. For predictive purposes, it often works very well. And so again, looking at training set sizes, so here I compare rich with alpha equal to 10, which was the optimum for, I think, for the 60 training set samples we had. And I compare it with varying training set size to linear regression. And basically, you can see if your training set is very small, using this penalty gives us a big improvement. Well, here, if you have 40 samples, you get worse than 0 errors with linear regression, but you get some reasonable results with rich regression. But if you have many samples compared to the number of features you have, they're basically indistinguishable. So if you have 1,000 samples and 3 features, then don't worry about it. And don't grid search your alpha, just use linear regression. If they're more similar in magnitude, number of features and number of samples, definitely try rich regression. So this is sort of the simplest way you can penalize linear regression to be more simple. There's another way that's very common, which is called lasso, which is an L1 penalty. Formula looks basically the same, except the norm that we are using here is an L1 norm. So before, we wanted the sum of squares of the coefficients to be small. L1 norm is the sum of absolute values. So again, we want W to be small. We want the coefficients to be small. But so because of fun kinks of mathematics, maybe, what this does is not only it pushes W towards 0, it pushes some coefficients to be exactly 0. I mean, you can think of this, the L1 norm is the convex relaxation of the L0 norm, or something like this. Or you can just remember, lasso makes coefficients exactly 0. And so this is great if you think most of your features are useless, or many of your features are useless. It gives you a way to determine which are the useful features. So if you automatically, so if you look at the, this was rich regression. Even if I set alpha to 100, which is pretty big, all the coefficients are non-zero. They're all not super big anymore, but all of them are non-zero. So my model is sort of hard to understand, and it depends on all of these features. If I know that the true coefficients, only a few of them are not 0, then I can use the lasso model and discover automatically which ones are true. This leads to a model that's easier to understand and much more compact. Again, I can do sort of a grid search for alpha or look at different accuracies for different values of alpha. Here, you can see again sort of the same curve. If you have very high alpha, you penalize the model a lot. Both training and test scores are low. If you penalize a little bit, then the training scores go up, test scores go up. If you penalize too little, you overfit. We can, but sort of to see, so this is very similar to what we saw in Rich. But if you look at the coefficients, it's quite different. So here you can see that if we set alpha equal to 10 or even to 1, a lot of these coefficients are exactly 0. And so when you write down the model, you know these features don't matter at all. And so here, maybe only half of the features were actually selected, or maybe even less, depending on the alpha parameter. Here's again what's called the learning curve, how well generalized as a function of samples. Here, lasso does better than Rich and linear regression. The main reason it's true here is because in the true model, we know the true model, and we know the true model has most coefficients 0. In the real world, you might not know this. So lasso mostly works well either if you really want to have something that's easy to interpret and has only very few non-zero coefficients, or if you actually believe the true model to be what we call sparse, to only have a few non-zero coefficients. In general, it doesn't perform better unless this is true of like the real model. There's another model that's linked to here that I'm not going to go into detail, which is called ElasticNet. ElasticNet has both an L1 and an L2 penalty, and so you have 2 parameters, and so basically you can interpolate between Ridge and lasso, and you can get the best of both worlds. And that's usually what performs the best in practice, but you need to tune 2 parameters. And again, if you have enough data, just use linear regression because it doesn't matter. Questions about linear models for regression? So now we're going to do the same thing again for classification. So in classification, we had a similar decision function, a linear combination, only we looked at the sign of the results. I wrote it here as greater than 0. So if it's greater than 0, I predict 1. If it's smaller than 0, I predict -1 or something. And so there's 2 models that basically implement this, logistic regression and linear SVC. And for the purposes of this class, they basically do the same thing. They have different loss functions, but I don't think we write them out, no. So if you're interested in the math details, one uses what's called a hinge loss, the other one uses what's called a log loss. In practice, I rarely found this to make a difference. The benefit of logistic regression is that it can estimate probabilities, while linear SVC cannot estimate probabilities. And both of these models, logistic regression and linear SVM, you can have an L1 penalty as in lasso, or you can have an L2 penalty as in Ridge. And here, for historic reason, the penalty is called C, and it's more or less 1 over alpha. So a large C means less regularization, a small c means more regularization. And I could have made the same plots as we saw above with the coefficients shrinking towards 0 if you increase the regularization. I thought that was kind of boring, so I made a slightly different plot here.
And here you have a 2D classification task, binary classification. And so on the left, C is small, so a lot of regularization. On the right, C is large, so less regularization. And you have the decision boundary as a black line. And so another way to think about it, except for pushing the coefficients towards 0, which I find hard to imagine given this 2D line, is it controls the influence of each individual data point. So if you look at this data set, you might say, oh, blue is at the top and red is at the bottom, which sort of overall is true. And but you have these two outlier data points, this one and this one, for which this is not true. If you have a lot of regularization, the impact of each individual data point is pretty small. So you have a more or less horizontal line which says blue is on top, red is at the bottom. If you decrease the regularization, you allow each individual data point to have more influence. And so basically the classifier tries harder to get each individual point right. And so if you set basically turn off the regularization, you get something like this, where you get now 1 point more that's correctly classified. So here we misclassified the red point, here we still misclassified the red point, here we classify the red point correctly. But now the decision boundary is much more crooked, and it reflects less the sort of more global layout. You can't, I mean, ideally you would try to also classify this one correctly, but that's impossible with a line. So you can think of the regularization either as pushing the coefficients towards 0 or as controlling the influence of each individual data point. So maybe a little word about how this works for multi-class classification. So I think for binary classification, the formula is pretty clear. For multi-class, it depends a little bit on whether you use linear regression or logistic regression. But in general, you can think about it as that's mostly true. Let's say the intuition is true, is that you build a model for each class versus the other classes. So if I use linear SVC, I will get, this will build what's called the one versus rest model. So here I try to classify the gray point with the other points, the black point with the other points, and the green point with the other points, and I get 3 models. And then the model that is most certain will make the decision, basically. So if I call fit here, I get a coefficient which is of shape 3 times 2. That's number of classes times number of features. So I have 3, for each of the classes I have a different coefficient vector. And for each of the classes I have a different intercept. And so here's a bunch of matplotlib code that we don't need to worry about too much. But why did we do the colors like this? I don't understand why we did it. Give me 1 second. I want different colors. What's it called? Is it called Vega 10? They renamed it again, right?
No at this point.
But they renamed it something, right? This name's deprecated? Does anyone know the real name? No matplotlib geeks here. Which ones? These two? This is green, this is orange. And wow, because I'm going to complain to matplotlib people because this is now the standard color map, and that's really, really bad.
It's not the standard color map. Here this is the standard color map.
For continuous.
Okay.
This is, if you plot multiple lines, it'll use this. Like if you plot 3 lines, well, that's not great. Thanks for pointing that out. Can someone make a note to complain to Tom or Ben? When Ben comes in the next time, we assault him, okay? You see the guy with the classes that comes in regularly? It's his fault. Anyhow, so here are the decision lines learned by these 3 different models. So you can plot the like the coefficients and intercepts for each of the classes, give you like a decision boundary, and basically the one that gives you the highest decision value, this will be the class. So basically, here this will be orange, here this will be blue, here this will be green, and sort of the boundary is in between these lines exactly. And so basically, you have you learned as many binary linear models as there are classes. And so, as an exercise, I want you to use logistic regression and classify the digits data set and grid search the C parameter. So C parameter, you should search on a logarithmic scale, so 0.001, 0.01, and so on. And see how that goes. You can also look at the coefficients if you want. And yeah, also change in the learning curves that we plotted above, so the plots where we change the number of training data points, how do they change if I change alpha? And so maybe you can play around this for like 5 minutes. All right, so let's look at the solution. So for the grid search, there's not really anything new. It's just sort of, so you practice more doing grid searches because you have to do them all the time. So we start by loading the digits data set. We split it into a training and test set. We probably should stratify it, which we didn't. And then we define the parameter grid. The parameter we want to search is C. So small c, high regularization, large C, less regularization. We instantiate grid search CV with logistic regression, parameter grid, and CV equal to 5. We fit it on the training data set, and then we compute a test score and the best parameter. So the best parameter was 0.01, this one, and the best test score is 97%. So we got 90% accuracy. And yeah, basically, whenever you use a linear model, you should always grid search the regularization and scale your data, except if it's digits, then don't. It's true.
The only data set for which you don't have to do this.
MNIST neither. No. So basically, if the magnitudes have semantic sense, or like the differences in magnitudes are semantic, then you shouldn't scale. But that's very rare. But it's true for these pixel things. So here, I did the same thing as above, the learning curves, and I just did logistic regression against Rich and Lasso with alpha equal to 1, alpha equal to 10, and alpha equal to 100. And so basically, if alpha is equal to 1, we have very little regularization. So Rich and Lasso mostly behave like linear regression, as you can see here. So they're like, they work somewhat better with less training data, but like the difference is smaller. With alpha equal to 10, it was the best results we got with grid search. They're both much better. So they get better results for all the data, for all the numbers of training samples, and they also get better results for like fewer training samples. If you set alpha very large, you have a lot of regularization. And so you can see that for both Rich and Lasso, for very few data points, they do pretty decently still, comparatively. You can see also that the training error is much, much lower. So they're sort of much more underfitting.
And if you set alpha too large, you can see here in the lasso case, it basically never learns anything. Probably all the coefficients are more or less 0 all the time, even if you have a relatively big training data set. So if you regularize too strongly, you might not get the same performance as if you didn't regularize. And here, even with rich, your performance is not as good. Alex, by the way? Yes. I think you can see here the difference of alpha scaling with number of samples, not number of samples from this plot, because it's not scaled with number of samples in lasso, and so it remains flat, where rich converges. Anyhow, you see it?
Long conversation.
Very long conversation. Don't worry about it. All right. More questions about linear models? Regularization, multi-class, anything? So, okay. So let's talk about trees. Trees work completely differently and are more or less the opposite of linear models. So trees are very highly nonlinear, and they can be arbitrarily complex. And so, why isn't there an image of this? So basically, decision trees learn to ask a series of if-else questions. So you learn to make a decision by asking a question. Here, there's like, you found an animal in nature, and the first question you ask maybe, is this animal bigger or smaller than a meter, or 3 feet for the Americans? If it's bigger, you ask if the animal has horns or not. And then you ask, are the horns longer than 10 centimeters? And so you narrow down which kind of animal could that be. And so the next question you ask depend on the answers that you had before. So this is a binary tree of questions. And sort of once you end up in the leaves of this tree, you get some answer. And decision tree is basically try to automatically learn this series of questions and what the right answers are, and what the outcome should be given the answers. So let's start with decision tree regression. So we have this sort of same data set with the sine wave and the slope that we had before for regression. And so the questions that decision trees ask are not really about animals having horns. They are about thresholds on features. So they always ask, is feature xi greater or equal threshold ti, or tj? Here, in this example, it's a 1D example. So all questions will be about the one feature. And so all the questions will be, is the feature greater than 0, is the feature greater than 1.1 something, and so on. And so the main parameter, or one of the main parameters of decision trees is the maximum depth. So by default, decision trees are grown until each leaf only has a single answer in it. So here the answer is the target value. So if I don't restrict the depth of the decision tree, I basically will have one value in each leaf, and I'll totally overfit the data. If I say max depth equal to 5, I'll do a binary tree until depth 5, and then I stop splitting. So basically, the way the splits are found is by a kind of brute force search. So you ask, what is the first best question? It tells me as much as possible about the data. And so actually, okay, let's look at classification. I think it might be a little bit easier to see there. So this is my favorite plot because I spent hours on creating it. And now it doesn't work because I zoomed in. Yes. Come on.
this 100%. All right, so let's try this. So you have a data set here on the left, which is like we want to try to classify red versus blue points. And so here we have two features, x-axis and y-axis. And so what the algorithm does is it tries to ask what is the most informative question I can ask, either asking a question about the x-axis or the y-axis. And it tries all possible questions, so basically all possible different thresholds or like axis parallel decision boundaries. And the one it found here is the first best question is to ask whether x0, so here the x-axis, is greater or equal than 0.996. That's this line. So this line is actually pretty good at separating red from blue. It's the best possible axis parallel line to separate red from blue. And so if you would stop here, then it would say everything on the right is red, everything on the left is classified as blue. And this is sort of a drawing of the decision tree. You can now keep going and recursively partition each side. So now again, you ask what is the best possible question to learn more about the target. And here on the left-hand side, you can split here, asking if x1 is smaller or equal minus 1.2.06. And, oh, sorry, it's actually the other way around. This is if x1 is smaller than 1.528. And if so, you're in the top here and you classify it as red. Otherwise, you're in the bottom here and classify it as blue. And similarly, you did the same on the other side. And so you can keep recursively adding more and more branches and keep splitting up the space more and more. So you can think of this as a recursive partitioning, where for each region that you have, unless it is already contains only one class, you ask, what is the best way to split it up more so I can learn more about the classes? And so in the end, you end up with this. So you can see here, you can sort of see the decision tree, and this is the result. This is somewhat overfit the data, because we didn't restrict the depth. It'll grow until everything is perfectly classified. So classify stuff here as red, and here, and here, and here, and here. And so you can see that there's a line of blue here and here that maybe you might not expect, or you might not expect the red here. So there's several ways to restrict these trees and keep them from overfitting. So one is the maximum depth, which you can like experiment here with the slider. Other possibilities are the maximum number of leaf nodes, or the maximum impurity, which basically says how many wrong points need there be in a region before I stop splitting. Okay, questions about trees? So maybe one thing about them is,
the way you describe that, it sounds like if you limit the depth, it won't really change the top part of the tree at all. It won't
no.
Optimize it in any way.
Yeah, because it's a very greedy procedure. You find the first best question, then for each region separately, the second, yeah.
Are there any packages that go back and prune?
I'm pretty sure there's packages that go back and prune, but not in Scikit-learn. Are you aware of?
No. So it's a regular question we have, and the answer is often in practice for prediction, which is basically the only thing that we bother. It doesn't really matter to prune. Pruning is mostly useful for simplifying the story about the model, but if it's just a matter of prediction, you don't really care.
Well, mostly because okay, so for the recording, question is, can we go back and prune? And the answer is, if you care about prediction, which Scikit-learn mostly cares about, you're not going to use trees, you're going to use random forest, which we're going to explain next, and then you don't need to prune. if you want a very easy and interpretable model, it's probably a good idea to go back and prune. And we both don't know of a package. But we have pull requests for Scikit-learn, and I think we should add it, but we don't have it right now. All right, so yeah, the thing is, decision trees tend to overfit quite a lot, and which is why people don't really use them a lot. Instead, what people are using is random forests, and what random forests are is basically just many trees that are trained on different subsets of the data. So here's another neat animation. So here, this is using many trees of depth 1 that are trained on slightly different subsets of the data, and then the aggregated results. So basically, each tree can give you probabilities for each region of the input and ask what is the probability of each class. We aggregate this probability over all of the trees. Usually it's a couple of hundred. And that gives you a much more robust result that's less likely to overfit. And so here you get, even for maximum depth equal to 1, you get a reasonable result here. And even if you increase the maximum depth, it's going to be like a little bit more spotty, but the result's much more reasonable than what we had with just a single tree. So the main way that, there's two ways in which the trees are made different. So there's randomization. If it was like 10 times the same tree, obviously it wouldn't change anything. So there's two ways the trees are randomized in a random forest. One is we take bootstrap samples of the data, which means we draw with replacement as many samples as we have in the original data set. So for each tree, I create a new data set that's as big as the original one, but some samples don't appear and some appear multiple times. So in expectation, about, I think, 66% of the data will appear in each tree. So this bootstrapping means that every tree sees different data, and so they will be different. The second way in which the trees are different is that in each node in the tree, we only consider a subset of the features to split. So that basically just adds some noise or randomness into the process and makes sure the trees are sort of different. So all the trees still overfit, but they overfit in different ways, and if we average them, everything is fine. And so random forests are really one of the best off-the-shelf methods, in particular because like trees, I should emphasize this, trees don't care about scaling. If you scale the features, it doesn't matter to the tree at all. It tries all possible thresholds on all possible features. So even if you do like a logarithm, it won't change anything. It just cares about the order of the points for each feature independently. And so any like transformation that leaves this intact, you can do a log, you can do a square root, you can scale. It doesn't matter to the tree at all. And this way, it's very robust to your representation of the data.
You said that if one averages a large number of these decision trees, that everything will be fine. Is there theoretical stuff for that?
Yes. Basically, I don't have the exact formula in my head right now, but basically, if all of them are better than chance and they're not very correlated, then averaging them will make it better. It's sort of wisdom of crowds. If everybody is right more than by chance, and we don't, and sort of there's everything's not perfectly correlated, then everything will be better in aggregate.
You can see this as a reduction of variance. If you average things that are independent, if you average two things independently, then you reduce the variance by 2. Okay, so, and since trees have a very low bias, if they are very deep, then basically they have very little bias in the predictions, but they can have a high variance. By averaging a lot of high variance but independent models, then you have a good average model.
I mean, in truth, they're not independent, obviously, because they're all sort of built on different parts of the data. But that's yeah, that's the general idea. There's a great paper that's like super famous by Bryman about random forests. If you're interested in this, you should read it. Yeah. So for random forests, there's 1 or 2 tuning parameters that you should care about. So there's one parameter that you need to set, but not to tune, which is the number of trees. Just more trees is always better. And so number of estimators, the number of trees, and you usually want to set it in a number of hundreds. If you cannot never use too many, but at some point there's diminishing returns, so everything will just take longer. So you can try out a couple of values, or you can take the biggest value that you're patient enough to compute. And maybe the most important parameter is how many features to pick. The standard value is that each node uses a square root of the number of features. So if you have like 16 features, each node will use 4. They're randomly picked. And so other options here, this is a digits data set, so I'm trying square root, which is 8, log 2, which is like 4 or something, and 10, which is just 10. And so this is one of the most important parameters that kind of controls how different the trees are. And the max depth basically controls the overfitting of each tree, but it also sort of limits the size of the tree, which means they're faster to grow and smaller to store. If you have a big data set and you don't limit the tree in any way, these can become really, really big. And so they can be and take a long time to build, and they can take a long time to load, or they just like gigabytes and gigabytes, and so it's hard to store them. So yeah, here I'm using grid search to search over a number of feature and a maximum depth on the digits data set. And so here, I'm actually not doing that much better than the linear model. I think I do about as good as the linear model. Let's see. So it uses a square root number of maximum features and maximum depth of 9, which was the biggest I tried. Maybe I should have tried a little bit more. But then obviously it takes longer. But yeah, generally this is one of the best off-the-shelf methods, and you should probably try this on whatever problem you have. I think I'm going to skip the gradient boosting, but just briefly talk about feature importances. So random forests can be a little bit hard to understand because there's like hundreds of trees, and is there no matplotlib inline somewhere? So, but there's one way in which we can summarize the tree somewhat. There's feature importances, which say how often was a feature selected and how important was it to select this feature in all of the trees. And so this aggregates over all of the trees how important the feature is in a tree. So what we're doing here is we're classifying the digits with class 1 against 1 and 0? Was it?
Yeah, 1 versus 0.
Oh yeah, sorry. Yeah, we classify digit 1 versus digit 0. And so then we can get the feature importances, which say which of the pixels are important to make the decision 1 versus 0. And so this has the same shape as the input. So there's one importance per each feature, and you can see them here. So basically, here, if you're in the middle, this is very important, and then there's sort of a ghostly like 1, this is very 0, that's very important. So if you have stuff here on the outside, that's important. If you have stuff very in the center, it's important. And that kind of makes sense because this is where the 1 is and where not a 0 is, and this is where 0 but not 1 have stuff. This is very similar to looking at the coefficients of a linear model, though here these just say it's important. It doesn't say in which if there's a monotonous relationship. If you have a coefficient in a linear model, it says a high value here means class X or class Y. Here you only say it's important for making a decision. It doesn't say it points in direction of this class. And you can't really say that because trees are very nonlinear, so there doesn't need to be a monotonous relationship. But still, it's a way to get out the important features. All right, questions? So, all right, that's it from me. I'll hand over to Alex.
Everybody's asleep. Yeah. I'm gonna speak slowly and quietly so they can stay sleeping. Okay. No, shout. I actually have a taser in my backpack, so if you can taz them like this. Okay, so you're still alive, right? So to make sure you follow, we're going to start from the end. So if you're not seeing the same thing as me, it's because you're not paying attention to what I'm saying. So what's about to pop up is notebook 22. So we just made a step forward in time, now at 22, and depending on how much time I spent on this, we might go back. So let me just plug this before it's too late. Okay, so the objective of this notebook is to tell you as much as possible about anomaly detection in something like 20 to 25 minutes. So I guess it's a very recurrent problem. I mentioned this morning. Very often people come to you and say, okay, here's my hard drive, here's the database, here's whatever, Excel spreadsheet. Can you find me something that looks interesting or I should be looking at, or something which is weird, that basically will spot something that is not okay with one of my sensors or one of my person in the that is supposed to be filling all these entries and these numbers, and that starts to maybe make mistakes when they type, or anything that looks bad and that needs action. So as you'll see, this idea of anomaly is kind of a fuzzy concept, but still at least two people have tried to define it. So let me just read this with you. So the first one is this quote from Johnson, which says an outlier is an observation, so a sample in a data set which appears to be inconsistent with the remainder of the set of data. Okay, so it's a really hand-wavy explanation. We'll try to see afterwards in terms of stats, in terms of quantified metric, how we can translate this to something that a computer can actually optimize or find. And the other one is an outlier is an observation which deviates so much from the other observations as to arouse suspicions that it was generated by a different mechanism. Okay, so the other mechanisms can be sensors getting bad or too old, or your operator just falling asleep. So there are different types of anomaly detection depending on the setup, and let me try to simplify all this. So we mentioned this idea of supervised and unsupervised learning. I would say the first one, which is not really the one that I'm going to cover afterwards, is the supervised anomaly detection. And it's typically a case where you have labels on both normal data and anomalous data, and you want to find a way to say, okay, this new data point is an anomaly. And really, what it really means when people think about a supervised AD is binary classification with one class, which is very, very rare. Okay? And everything you've heard today about binary classification, you could apply in this setup. It's just one setup where one of the class does not appear very often. The two more interesting setup are the semi-supervised and completely unsupervised AD. So when people speak about semi-supervised anomaly detection, it means that they have access to data, and they know that in this data there's no anomaly. Okay, it's only clean data. So they have access to an entire distribution of data in which they know there's no issue. And in some sense, it's better than nothing, and that's why people call it semi-supervised. The nothing would be, here's all my data, there might be some anomaly in it, I don't know what fraction, just find me the ones that are weird. And this setup is really the tough one, and this is what people call unsupervised AT. So you have data, some of them are good, some of them are not good, just find a way out. The only assumption is the fact that anomalies are rare. That's the only thing that you can, that you need to assume in order to be able to do anything. If the anomaly are half of your samples, then there's no way you can figure out something, okay? Maybe you can do clustering and see if you have two clusters, but what is an anomaly doesn't make any sense if it's not rare. So let's see what this can all mean. So I'm just going to generate some data with the make blobs and just show you how it looks like. Okay, so I've got two blobs of data, and so I've got some high density regions which are the center of the blobs and some samples which are quite off. Okay, so I've got a fraction of point which is just due to random sampling are away from the mass. Okay. Here, on purpose, I didn't simulate with only one blob, okay? We could just simulate with only one blob, which would just be a Gaussian blob. But you can apply anomaly detection in much richer context. You don't have to have only one blob of data to find out. So let's try to see how we can convert this idea of anomaly in the context of stats. If you think about something which is rare, you can see this as a point, a sample for which the probability of sampling this point is very low. Okay, so it was really unlikely to observe this point given the distribution of normal data. So if you think of it this way, it means that you can just try to estimate the density of your data set, and then once you've estimated the density, score every sample by the probability of observing each of these samples. And if the sample has a very low probability, then it's rare, and somehow this probability can be matched as a quantified number of anomaly, okay? So let's see how we can do anomaly detection with kernel density. So I'm going to use the kernel density estimator that you find in neighbors.kde, and which basically is, as any scikit-learn estimator, has a fit method. And here you see I only fit on X. There's no X and Y. I just fit on my entire data set. So you see it's pretty fast. I mean, the data is very low dimensional. I only have very few points, kind of super fast. And what I can do afterwards, in order to get access to the log probability, something that should be what I'm interested in order to do anomaly detection, I can use these score samples. So these score samples is actually a method that gives you a score, which is not a single score as the score function, the score method that you've seen so far. It gives you a score for each of your samples, which means that if you have 100 samples as input, you're going to get 100 values out.
So this is exactly what you see here. My x was actually 500 by 2. So let me just illustrate this. And if I do score samples, I get 500 values, which are the output of the score samples. And score samples contains the log likelihood of the data. Okay, so the log of a probability of observing this sample under the density estimated during the fit. Any question? Okay. Do you know any other method that would be good for estimating a density? Any idea? Okay. Sorry? You could use a histogram, okay, and you can basically, that would be a completely non-parametric way of doing things. You bin, and then you find every point that falls in a bin, which is very low, very few bins in this histogram bin. Then it's somehow also a measure of density and anomaly detection. One issue with these histograms is that if you're going to go in high dimensions, then the number of bins will go exponentially, and you might go into troubles. There's other models that we did not mention so far, which are called Gaussian mixture models, which are typically a way to describe your data as a mixture of Gaussians. Okay, there are other types of, and that would typically be super adapted to the data generated with the blobs. Okay, so all these density estimation methods basically can give you this number of rarity, how much is this likely, and action this into anomaly scores. So here I'm just going to use this mQuantiles function from a SciPy stats, which will allow me to make a nice figure in order to illustrate the decision function that says if I'm inside these circles, I'm in a high density region. So all the points that fall inside these regions, these two blobby red curves, if I fall inside these circles, well, blobby curves, they are not circles nor ellipses. They look like ellipses, but it's just the data that make it so. I'm a normal observation inside, and otherwise I'm outside. Okay? There's, here I said that the quantiles at 95%. It means that I constructed the data so that there was 5% of points which are outside and the rest is inside. What this pretty much tells you is that there are two kind of parameters that appeared here. One which is very explicit, which I just mentioned, which is the fact that you assume that only 5% of the points were outside. So someone has to tell you, if you need to decide this is anomaly, this is not, you need to set a threshold about what fraction, what's the contamination level of your database. Okay? You can keep the continuous value, and then you can probably start by looking at the points which have the lowest probability, so the more likely to be an anomaly. But if you need to threshold, you need to threshold based on a fraction, a percentage of anomaly that you can assume on your data. It can also be based on the fact that if you have 1 million samples and it takes 1 hour to look at one sample, and you have only one person that works 8 hours a day, probably less if you're in a very socialist country like France. Try to make jokes to wake you up. You need to basically adapt this budget of what's the number of samples that can people look at in order to calibrate what's the contamination level that is realistic. Okay, otherwise you're going to have a lot of alarms, and if an expert needs to look at all these alarms one by one, that can take a lot of time. So this was the explicit parameters. There's another one which is super critical. Any idea what implicitly I assumed when I looked at densities? Somehow when I just use a KDE, so this is non-parametric, but somehow I use still a Gaussian blob around each of the samples. So that probably points you in the right direction. Okay, I use a Gaussian blob, which is like a circular isotropic blob around each of the samples. So let's say if I scale my data, I stretch the data in some directions, what's going to happen? Is it going to change the output? It depends how you quantify the size. If the size is completely based on Euclidean distance and you scale the features differently, then the Euclidean distance doesn't mean the same thing. So the implicit thing that is behind this is that I assume that to look at density, I had a ground metric, and this ground metric was the Euclidean distance. Okay, this is something that is very common in many methods. You had the issue this morning with k-means. All these methods, I mean, k-means, this one, these methods rely somehow on a way to compare samples. How far are they from each other? You cannot compare, you cannot evaluate densities if you don't have a notion of measure or what's the volume, what's the distance between your points. Okay, so just keep this in mind, because if the metric doesn't make much sense for what you're doing, think about doing anomaly detection, and you have categorical variables, then you have things that are in continuous metrics. You might have to think a bit how to do this. Yes?
Is variable density also going to be a problem? Because you've got also involved in variable density, the non-linear compared with.
Yes. That's a very good point, and there's an algorithm that is called local outlier factor, which is exactly addressing this issue. And it's merged, probably, but for sure there's a PR that's about to be finished, or hopefully. So.
What if it's not a blob, like some number which, it's a growing number, the next number is bigger than the number, so some sort of a function or a formula.
So the question is, what if it's not blobby? What is not circular? So here, when I use the KDE, this non-parametric way of estimating densities, I did not really assume that there were blobbies. So you just see as a way to, I mean, we could probably do an example with the two moons, which is a classical nonlinear, like non-blobby types of simulated data, where you would see how it adapts to the curvy shape of your data, for example. All right, so historically, there was a very popular method that was proposed in the late 90s, which is called one-class SVM. So SVM, you haven't heard about them today so far. They are really the new kids or the old kids on the block from the 90s that were very much studies in terms of math and also algorithms and implementation, how to train these types of models. And so they have had their time where they were extremely popular. And one-class SVM is basically an extension of the binary SVMs to the case where you only have one class, meaning that you are in unsupervised setup. Okay? And the idea of one-class SVM is to basically try to find a decision that can be nonlinear and based on kernels, like regular SVMs, and to have a decision function which is sparse in the number of samples, meaning try to find a few samples that allow me to separate what is inside and what is outside. One-class SVM takes as parameters a new parameters which controls this fraction of contamination. Okay. So when you use a one-class SVM, you need to set the new, and typically, if you set the new, if you do it by the books, as the theory tells you, if you know that you have a 5% contamination, your reflex would be to use 0.05 for the new parameter. In practice, we can discuss a lot about why it may not be a good solution when you are in finite dimension, finite sample size, so you only have a limited number of samples and not an infinite number. But at least what the theory tells you is that you should use 0.05 if you are trying to find the decision function with 5% anomalies. So this one class SVM, again, you can fit them and you can predict, and it will predict +1 if you are okay and -1 if you are an outlier, an anomaly. So let me just illustrate this. Here, all the red dots are the points which are actually outside of the decision function, the decision boundaries, and are outputted by the one class SVM. So here it looks very similar to what you got with the kernel density estimation. What you can show, or what you can read also, is that KDEs will fall apart in high dimension. If you try to estimate the density of your data set in high dimensions, basically in high dimension, the space is completely empty. Okay? Even if you have a lot of points, if you're in a very high dimension, the space will look empty. So estimating a density when you have an empty space is really hard. So rather than estimating a density, which is kind of the, if you have a density, then you have a good way of scoring anomalies. But probably if you want to do scoring of anomalies, you don't need the density. You just need a decision function that tells you if you're small or if you're high, then you are an anomaly. And this is a much weaker thing to estimate than to estimate the true density. And one class SVM is a way to estimate this decision function, and typically will work better in high dimension than the pure KDE estimator. So it's kind of doing the same flavor of models. Okay, it's also based on local Gaussian kernels, this isotropy, but since you have this regularization by the sparsity of the samples, it would tend to scale better when you're high dimensions. Okay. So support vector machines have this notion of vector or support vectors, and these typically the support vectors are related to the point which are anomaly. And here, for example, I'm plotting them in a fancy color map that hopefully colorblind people can see. A tiny exercise for you that so you realize the difficulty of doing anomaly detection and why it's not so easy problems is try to rerun this exact same code by changing the gamma parameter. The gamma parameter is basically the bandwidth parameter on the kernel. Okay, it's just one parameter. And just try to change it and see how much the story changes. Yes?
Just a quick question. Wouldn't it be very similar if I basically measure the distance to the center of mass and I just reject 5% of the points?
So the question is, can I just compute the center of mass and remove the samples which are far from the center of mass? If you do something like this, it's basically assuming that your data is a circular blob, isotropic blob, and you model the data with just an isotropic Gaussian distribution. And then what you're describing is pretty much equivalent to what a proper model with Gaussian model and distance would do. These types of models can adapt to things that are really curvy, that have multiple modes. What you describe would not work if you have two modes. So you see the impact of the gamma, see how complicated your life can be. Just, you want a couple more minutes, or I can continue? Continue? No objection? Okay. So here I'm showing you the result with a very small gamma and a very high one, a much higher one. And you see how the story gets complicated. If you use a very low gamma, then you have a very wide Gaussian kernel, and you end up modeling your data with just one big mode. Okay? Whereas if I'm here, I put very tiny islands around each of my points. I end up with a very complicated decision function. Okay? So even if the theory tells you that nu should be 0.05, the gamma will change completely the story. Okay? So, I mean, there are ways around this, and there are strategies to tune parameters, and very recent literature on this. I'd be happy to talk to you about this. Just be aware that I mean, this is a critical parameter. Okay, so this is really all nice. And now I'm going to show you something that was added in the latest release version of Scikit-learn, which is called isolation forest. Isolation forest is actually an algorithm that is not extremely recent, but has not very much, has not been used very much because it was lacking a good publicly available and documented implementation. But still a very powerful method. So the idea of isolation forest is to use trees for anomaly detection. So as you've seen with the previous notebook with Andy, trees are extremely powerful methods. They are basically trying to split the space in tiles, and inside of these things, then basically divide the space, and this is what people call partitioning methods. Okay, you partition the space by just making split along the axis directions. The idea of isolation forest is to say, if a sample is away from the mass, I can isolate it very easily in a very few decisions. By very few splits, I can isolate the sample. Typically, if I'm in the x-axis and I've got one point which is far, I just need one split to say, okay, now you're alone. You're isolated. Okay? So now you do the following strategy. You build trees that are completely random. Okay? So you build a tree, you take a random features, and then you take a random threshold. If you do this, and your point is just in a rare location of the space, it's very likely by doing this random split that you're going to isolate a sample. Okay? So the idea is to build a forest of random trees and see on average how many splits do you need to isolate a sample. It's kind of a natural and smart idea, I would say. And the nice thing about isolation forest is to basically come up with one number that converts this intuitive explanation to a level of an anomaly. Okay? So they have a way to pool this level of anomaly from a bunch of trees and to convert the depth of the trees into a number that seems to be right stable across trees. So let's see how this behaves. So this is the same data as before. And here, I'm just using trees, but I'm using actually a lot of trees. Just to show you that there are actually trees, I'm going to take much less of them. And if I take only 30, then I've got a more chaotic boundary. This is still too nice. Let's say I do 10. You see that you have a rather noisy behavior. So by adding a lot of trees, you regularize the decision function. Okay? So let's go back to 300. So let's skip this exercise because I just did it for you in real life, in real time, which is to look at the influence on the trees, on the number of trees. So very little number of trees, then you have a noisy boundary. If you have a lot of trees, you'll seems nicer. So maybe a question for you is there any reason why you should not use too many trees? In other words, does it make any sense to cross-validate the number of trees? Or find any types of reason why you should do 300 trees rather than 500 trees. And this is a question that also applies to random forest. If you understood what I briefly said about this idea of bias and variance, you should be able to answer this question. Yeah, so there's, if someone tells you I use 300 trees instead of 5,000, the only good reason for doing this is running time, for training and for prediction, okay? Even though you can do the training in parallel, you can do the prediction in parallel, you still burn a lot of CPU time by adding more trees. Now, what the theory tells you is that the more trees you have, the better, okay? But maybe it's enough to have 300 and you don't need 5,000. Or the gain by doing to 5,000 is negligible, but in terms of running time, that's a lot of time, okay? So here is the same logic. You're doing isolation forest. The more trees you use, the better it should be. But at some points, I mean, your patience has limits, at least mine. But okay, so keep this in mind. Typically, you increase the number of trees, keep the running time reasonable for your application, and see at some point when you add more trees, the results are not going to change much, and that's the time to stop. So let's try to do a real-life applications of anomaly detection. So we're going to use, again, the digits data set. And the game is, can we use what we've just seen to figure out what are the digits that are weird? Okay, so the digits that are not properly drawn or that looks suspicious. Okay, and let's see if all these fancy algorithms can spot digits that actually look different from what a 1 would look like or a 5 would look like. Okay? So again, so we load the digits. We have this amount of samples, 8 by 8, so 64 pixels. This is just showing you one number, a 5, that looks a nice 5. And what I'm going to do here is reshape this. I have 64. And here, I'm going to focus on the 5. Okay, don't ask me why 5, because 5 is a good number. 42 was not in the data set. And you'll have all your time afterwards to try all the other numbers. It's actually the exercise that is just below. So here, just use fancy indexing to get from the data the images that correspond to all the 5. Okay, so that's why it's called x_5. And now I've got 182 images of 5. Okay, let's look at a few of them. Okay, so this is the first five from the data. Typically, you see that the first one looks not too much like a 5. And the other ones look nicer, okay? So let's use isolation forest to score each of these images and see which were the ones that are the most normal and the ones that are the most anomalous in the sense of isolation forest. So I'm just going to fit the model here and just use then the decision function. So the decision function is basically giving for each of these samples the score of anomaly, okay? And the idea is that the lowest is this number, the more the sample is an anomaly. So typically, all the points that are in this part of the histograms, all the images that are in the part of the histograms are the normal points, and then you have a few weird samples that are here, okay? So since it's digits, I can look at them, which is nice, because I can visually assess, as an expert in writing files, how they look like, okay? And so these are the 5 that are the most inliers, okay? So they look all like nice 5s, okay? And now I can do the same thing with my outliers. And here are the 5 that look weird. And at least if you are experts in 5 like I am, you agree with me, okay? They are weird, okay? So it's magic, okay? It's machine learning. It's amazing. And we found the bad 5s. And now your mission, if you accept it, is to do the same thing for all digits. Can you find me the bad 0s, the bad 1s, etc.? And does it work? Or just 5 was just a good number? Couple more minutes. Good? Move on? Move on? All right. So just execute this and see. So this is going to give me the weird ones. And you can just change the value of k, and you'll see the other digits. Right. One word about local outlier factor. This is not released. This should be released in the next few days, provided we find the time to do the pre-release and get everything fixed and merged before the final release. But it's still, if you have the dev version, you can play with LOF, which is also a very powerful method. And LOF is anomaly detection using nearest neighbors. So eForest, iForest, isolation forest was anomaly detection with trees. The other one was anomaly detection with kernel methods, and LOF is anomaly detection with nearest neighbors. Okay, just if you just try to organize this in your head. Right, so now I'm gonna jump back in time and jump to number 20 and show you more advanced clustering methods, including dbScan, because I think dbScan is cool. So, you all with me, notebook 20? We just have 18 minutes left, so stay with me. Right, so we've seen so far k-means. K-means is interesting. What you need to provide as k-means is what? Is k, exactly. And k stands for the number of blobs, the number of clusters. Turns out, if you do clustering, you have 2 ways of parameterizing the clustering algorithms. Option 1, like k-means, you set the number of clusters. And option 2, you set some kind of distance or bandwidth parameters that says, if samples are less than this, then they should be in the same cluster. If they are further away than this, they should be in different clusters. And by setting this more distance parameter, then you don't control exactly the number of clusters. You just let the algorithm do what it can, says, okay, if the bandwidth is too big, then you have very few clusters. If the bandwidth is too little, then you have a lot of clusters. Okay, it's just 2 different ways of parameterizing your clustering algorithm. So typically, dbScan is the other family. We're going to need to specify what does it mean for 2 samples to be close. Before doing dbScan, I want to show you something that is very old but still very much used, which is called hierarchical clusterings, and makes these fancy graphs that people call dendrograms. So let me try to illustrate what hierarchical clustering does. If you want to do clustering, you basically have 2 approaches. Either everything is connected and then you start splitting stuff. Okay, so you subdivide, you have 1 cluster and then you subdivide. That would be a top-down approach. Or you have another way, which is at the beginning, every sample is in its own cluster, and then you start merging stuff in order to reduce the number of clusters. Okay, and this would be typically a bottom-up approach. Hierarchical clustering is exactly of this family. You start from all your data, and then you need to find a way to say, how am I going to basically glue things together in order to collapse all my samples and reduce the number of classes? The rule that you use to say, okay, this sample should be squashed into 1, how do you decide this makes the different types of hierarchical clusterings that you can have. So let me illustrate this with this graph. Imagine you start from the beginning, you have 100 samples, and all of the samples are 1 cluster. So you have 100 clusters, and you need to find a way how are you going to merge the first 2 samples in order to have not 100 clusters, but 99? Okay? The most obvious things to do is to say, I'm going to find the two samples which are the closest to each other in terms of Euclidean distance, and they're going to be one cluster containing 2 points, 2 samples. And then you need to move on. But then you need to find a way to say, what does it mean for a cluster to be close to another cluster? Okay, because now you have 99 clusters, but some are just 1 point, and some are multiple points. Option 1 is to use what people call single linkage. And you say that the next things that needs to be, the next cluster that needs to be merged are the ones for which the minimum distance between any of the points is as small as possible, is the smallest. So this is illustrated here. I've got 2 clusters. I evaluate the distance between, the minimum distance between every pair of points, and the clusters that have this minimum distance gets merged, okay? And you continue like this. So this is what people call single linkage. You can also do complete linkage, which is doing somehow these opposites. You merge clusters when the biggest distance between any pair is the smallest, okay? It's just a different way of deciding how to merge stuff. You have another one which is not illustrated here, which is called WARD, or ward clustering, W-A-R-D, which is something which is based on variance. This is not a min and a max, but it's mostly based on a criteria that is closer to k-means, which tries to have blobs that have low variance. So let's see how this behaves. I'm going to take my iris data sets, so now that you know very well, probably too well. And I'm going to use hierarchical clustering. I'm not going to take it from Scikit-learn. I'm going to take it from SciPy. So SciPy has a cluster module, and inside they have a submodule called hierarchy that contains a linkage function that computes the clustering, and then a dendrogram function that will allow you to plot it. So let's estimate the clustering and use the dendrogram to plot it. Okay, so this fancy picture just shows you how the different samples were merged, okay? Starting from the beginning, so that was typically done by aggregation from the beginning. You can use another criteria, which would be this. It would find a different tree, okay? You can use a different metric. So here, everything was based on the Euclidean distance. You could potentially decide that Euclidean is not what you want to do, and you might want to change this metric parameter. Right, so now if you want to stay in the world of scikit-learn, in order to, for example, get as prediction the integer like for k-means, there is this agglomerative clustering estimator that you find in the cluster module that implements this. So if I do, for example, complete linkage using Euclidean distance, then I can do fit predict like I did with k-means, and then I get the prediction, which is the class label or the cluster label for each of my samples. So here I set the number of clusters to 3. I could have used something different, but just to illustrate how it looks like, well, it looks a bit similar to what we had just before. Just the colors, again, are different. Same reason as what happened with k-means. And you see here that I had some yellow that are where in the green ones. Here, everything is very well separated, okay? No surprise. We've got 11 minutes, so. DB scan. So I'm not sure I'm keeping the best for the end. But DB scan is still a very powerful method. So it's not that old. I mean, there's a lot of things that you've seen with us today that are quite old stuff. DB scan is surprisingly was proposed not so long ago, and is not very much taught in ML courses. It starts to be, probably because it's in scikit-learn. but it's actually something that you should give it a try. K-means is not the only way to cluster samples. Take home message. So the idea of dbScan is the following. You need to provide as input a radius or bandwidth or a distance parameter. And you're going to say a point which is surrounded by X number of points that we're going to be calling the min PSTS, the min points, which are here. So here, if I, for example, say min points is equal to 3, this point here that you see, the blue square, is surrounded by 3 points that are within a certain radius. So this is going to be a core point. Okay? Basically, he has samples, enough samples at a minimum distance, user provided. This one is also a core point. This one is also a core point. Now, this one is another type of point which people call a border point. A border point meaning that it has samples within the radius, but it doesn't have enough. Okay? So typically, there are points that are going to be at the border of the clusters. Makes sense. And then you have some points which are noise points that are neither core points nor border points. And basically, what dbScan does is it samples a point from your data set, and it tries to grow the cluster until it has, it sees core points. If it has a core point, it continues. And when it sees a border point, it stops. That makes one cluster. And then it tries to sample a new point that is never seen. So you start to grow one cluster. Then you stop if you end up with only border points. And then you continue. And if you sample a point which is just a noise point, then you keep it as a noisy point and you move on. Okay? Seems super simple, intuitive. And let's see how well this works. So this is the typical 2 moons dataset that I briefly mentioned for anomaly detection. So I've got 2 moon structures. And what I'm hoping to recover with dbScan is one cluster that would be like this and the other cluster that would be like this. And you see that the clusters don't look like blobs anymore. Okay? They can have a very complex shape. And so this is now the output of dbScan. Yellow is one cluster, green is another cluster, and these 3 points in darker color are actually noisy points, noise points. They are outliers. Okay? So now you might want to change a few things. For example, if you change epsilon and you take an epsilon which is much bigger, what's going to happen? Only one cluster. Okay? Because everything is connected to everything with enough neighbors. If I use an epsilon which is smaller, then I've got tiny clusters. Okay? So pick a good value. Take home message. So let's see now. So this exercise, and you have 7 minutes to do it, is try to apply k-means agglomerative clusterings to these 2 circles data sets and see which one works and explain to me why it doesn't for some of these models. So let's execute this and see how good the different models are. And you see the first one is k-means, and you see that k-means fails. K-means, you've seen this morning, k-means tries to find some isotropic blobs. Okay? So the way to separate these samples into isotropic blobs is basically to draw a line in the middle, and this will not capture the structure, the complex structure that you see here. Same thing for hierarchical clustering. You try to merge things according to a certain Euclidean distance. Typically, the linkage can have a strong effect on this. That might help you a bit here. But clearly, dbScan is the one that gives you the good value. Now, if you screw up the value of epsilon in dbScan and you have because you have bad luck, you have one sample which is in between that allows you to connect the two circles, it's going to fail also. Okay. So we're about to conclude. We have 2 minutes. I just want to take 2 minutes to tell you what we did not have time to do. We didn't do 19. 19 is on feature selection. So imagine that you have too many features. You want to know what are the ones that are the most predictive. Which are the features that have the most discriminative powers. This idea of selecting the number of features can be motivated by production constraints. If you're in a business, when one feature is multiple terabytes of storage, maybe you don't want to work with all the features. You want to subsample, because otherwise storing all the features is too much. And you want to select the ones that are the most predictive power. And so there are ways to do this. Just look at the notebook, either in a univariate way or multivariate way. The other thing we did not do is nonlinear dimensional reduction. So maybe I can just show the figure. Oh, they are not rendered here. So it gives you an idea of what you missed because we were too slow. Let's illustrate this with digits and showing you how you can represent the digits in low dimension using either PCA. So you see that the cluster, the digits are a bit overlapping. There's no clear distinction, but still it looks in 2D. And yes, the zeros are far from the ones, and there's still some cluster that emerge. But actually, if you do it with t-SNE, which is a fancy nonlinear dimensional reduction method, that in the next release will be even better than the implementation that you have now, that is slow and will not scale, but hopefully this is fixed, at least in a PR about to be merged. You see that t-SNE can isolate the digits completely in an unsupervised way. Okay. So of course we pick the values of the parameters that make the picture nice. It's still unsupervised problem, so it means that there is a parameter somewhere, and in practice you need to find a good reason why you pick this value. Okay. And so just going back here, the other thing we did not mention at all is how you use Scikit-learn to do out-of-core learning. If you have a lot of data that don't fit in memory, can you still use Scikit-learn? And the answer is yes. There's a bunch of methods that allow you to learn a model by using mini batches of data or stream of data, where you see data as they come, or you read them progressively. You read some data, you update the model parameters, you trash the data, you take some new data, and you learn what we call online. Okay. This idea of online learning is the right way of scaling your learning to very large data sets. Not all methods, not all algorithms can do this. In Scikit-learn, some can do. They have a partial fit method. Partial fit because they can be fitted with a fraction of the data. Okay, so a partial fraction of the data. And basically this example is telling you how you train a model for text processing when you have a lot of text and you're going to read text as in mini batches and learn progressively. I think that's it. All the rest, we've done it. Of course, we have a very extensive online documentation. You probably have seen it during the day. There's a lot of things that you can read. You can read the book of Andy, which is a lot of stuff about Scikit-learn and more. And there are plenty of books in the PyData world using Scikit-learn that are worth exploring. And I think I'm 2 minutes late, so I will stop here. Thank you very much.